Today, we are pleased to have a presentation by Toru Fujii from Nikon. The title of the presentation is Practical Parameters that Affect Quantum Annealing, Convergence, and Optimizing QUBO Generation Parameters for NP Problems. Impact on material convergence. Okay, so Toru, please start your presentation.
Okay, thank you, Chairman. Hello, everyone. I'm Fujii from Nikon Corporation. I'm grateful for the opportunity to present my research at the INQA seminar today. So, well, title was introduced from Kadoaki-san, so I will start my presentation. Okay, the co-researchers are as follows. And first, well, we will investigate the effect of the transition rate between states during the annealing time evolution and the eigenvalue difference between the ground state and the first excited state are called the minimum gap, which is included in the convergence theory formula. Well, in a natural machine, there is a scaling of the electrical system. So the ratio of the maximum and minimum eigenvalue differences and the gap is important. And we call it the dynamic range of eigenvalues here. Simulations show examples in which the annealing time required for convergence can differ by several orders of magnitude, even for Ising problems with exactly the same eigenvalue intervals. However, published papers and our results show that the probability of occurrence of hard instances is small when the problem size is not so large, and as a result, we simplify the criteria for convergence difficulty and call only the dynamic range of the final state the dynamic range, which is used as the problem difficulty parameter. In the second half, we will explain the parameters and the convergence used to generate QUBO from NP problems. It will be shown that it is important to balance the size of the restrictive terms in the parameters of the QUBO generation formula within the range in which the dynamic range is maintained. Well, there is a large difference in the complexity of the graph coloring problem and the parallel machine scheduling problem used in the example, but the basic approach is the same. By uniquely determining the generation parameters, the relationship between the problem scale and the convergence of D wave becomes very straightforward, and we will also introduce the possibility of introducing it to problem evaluation. Quantum annealing was proposed by Dr. Kadoaki, well, today's chairman, and Professor Nishimori in 1998. And they stated in the paper that quantum annealing has a higher probability of acquiring the ground state when annealing with the same schedule as simulated annealing. In 2000, Fujii stated that according to the theoretical formula of quantum adiabatic calculation, the annealing time to bring the ground state convergence probability close to 1 must be inversely proportional to the minimum eigenvalue difference between the ground state and the first excited state evolving during the annealing time, and proportional to the rate of change between the ground state and the first excited state. First, let us look at the speed of change between the ground state and the first excited state, which is difficult to directly imagine as an energy landscape. Here, we compare the presence or absence of anti-crossing, which is closely related to the speed of state transitions. The results of a quantum annealing simulation with very strong anti-crossing are shown on the left. The vertical axis shows the convergence probability of each state. The horizontal axis is the normalized annealing time S. Green is a ground state, which ultimately has a probability of 1. The Ising program of the right is shown in the table in the center, and is a case when the eigenvalues do not change at all, and only the combination of states and eigenvalues can be changed from the left. As you can see in the right figure, the transition speed is reduced by an order of magnitude. Although we will not explain it here, this can be achieved by applying a unitary transformation called ELTIP to the Ising coefficient. As shown in Farley's convergence condition formula, the impact of the speed state transition is large, as will be shown in the next slide. The next slide shows that there is a difference not only the state transition speed, but also in the minimum gap. Here are another quantum simulation results for the problems on the previous slide. The quantum annealing convergence time are shown in the graph above, and the eigenvalue difference between adjacent states, that means gap of neighbors, during time evolution is shown in the graph below. In both graphs, the green is a ground state. Theory shows the annealing time at which the ground state convergence probability approaches 1. Comparing the upper graphs on the left and right, we can see that there is a difference in annealing time of nearly 4 orders of magnitude. If we read the values needed for Farley's formula from the previous slide and the graph above, we ultimately get the same results. Anti-crossing narrow the gap and increase the state transition speed during the annealing time evolution, which seems to be hindrance to convergence itself. However, if there are no anti-crossings, the final state gap could be simplified as a minimum gap. We will show in the following slides that the probability of this phenomenon, anti-crossing hard instances occurring, is not high when the problem size is not so large. We summarize the conditions for anti-crossings to occur and examples of the probability of hard instances. In choice example, a delicate tuning of parameters Ising coefficient is required to intentionally cause anti-crossings. We have also reproduced it. Crosson et al. And Boisho et al. Have shown examples of evaluating many problems. They have shown that the probability of difficult problems and hard instances is extremely low. Boisho has also shown that instances become difficult when the excited state has an eigenvalue close to the ground state and its Hamming distance is long, which is consistent with our simulations of small-scale problems. Furthermore, among the many parallel machine scheduling problems we generated, there were no problems that stood out as being particularly difficult compared to the others. This works for the moderately sized instances we currently handle. But as Altschuler points out, Anderson localization may make adiabatic quantum optimization fail for the larger instances we will handle in the future. However, in that case, the discussion of optimum parameters when generating a QUBO would become meaningless. In a previous slide, we showed that it is likely that in many cases it is safe to assume that the dynamic range of the eigenvalues of the final state determines the convergence when the problem size is not so large. From here on, we will refer to the dynamic range of the final state as the dynamic range and focus on it. Furthermore, it will be shown that we only have to do is to handle the NP problems by considering the dynamic range with the eigenvalue of the final state. Therefore, we will simplify the convergence criteria for the problems we dealt with today. The next slide shows that the D-wave convergence results depend on the dynamic range of the Ising problems. In order to see what happens when the dynamic range of the Ising problem is changed in D-wave, a small number of spin problems, in this case 4 spins, was used. And the eigenvalue difference between the ground state and the first excited state was changed by adjusting the Ising coefficient manually, and the convergence number of the ground state and the first excited state was plotted as a function of annealing time. D-wave's auto-scaling function was also used. The dynamic range is expanded from the left to the right. Here, the gap between the ground state and the first excited state is made smaller. The annealing time on the horizontal axis was changed from 1 to 20 microseconds. When the dynamic range is small, the probability of the ground state on the vertical axis increases slightly. But as the dynamic range increases, the two states are converging toward equal probability. This makes sense if you think of the gap becoming indistinguishable in the electrical system of a needle. Regarding to dynamic range and convergence probability of D-wave, Mücke et al. Provide useful graphical representations of the data. Now we focused on generating QUBO coefficients for the following 3 problems from Lucas's NP problems. Graph coloring problem, GCP, clip vertex cover problem, CVCP, and integer job scheduling problem or parallel machine scheduling problem, PMSP. For the future problems which become larger in scale, we prepared trivial problems where the correct answer state is known in advance. The calculation of optimal parameters for GCP and CVCP is very similar, so we will omit it here. CVCP is described in the preprint below. For a bipartite graph, the minimum number of colors for a GCP is 2. And for a complete n-partite graph, the minimum number of colors is n, making this a trivial problem. Well, because it is possible to swap the swap spins of the same color, or to swap groups of spins of the same color, the degree of degeneracy becomes very high, and the number of correct solutions, in other words, the number of ground states increases exponentially with the number of spins. This is later shown by the high D-wave ground state convergence probability of GCPs. Well, B is a result of solving problem A using greedy algorithm. It will always be incorrect because the job elements were arranged in an order that would fool the greedy algorithm when the problem was generated. C is a correct solution with the shortest makespan, arranged in an order that would fool the greedy algorithm. The greedy algorithm stacks elements from the bottom up in order of size, and then adds larger elements to the smaller number. But because this is done in reverse, it is unable to make the numbers add up and at the end by the greedy algorithm. D is another correct solution with the shortest makespan. C and D are also correct when all jobs are swapped between machine 1 and machine 2. However, the number of correct solutions is far fewer than the enormous degeneracy of ZCP. Using three-color graph coloring problem for tripartite graph, where the correct answer is trivial, we explain the eigenvalue difference between the ground state and the first excited state, which we will call the gap here, and maximum and minimum eigenvalue differences. For ease of understanding, let's fix B to 10, and also consider the gap for A around 10, starting from the smallest when A is 1. The first excited state is a correct answer with one node color removed. When A exceeds 2B, 2B becomes the minimum gap. The maximum eigenvalue corresponds to an extraordinary state with penalty. In other words, it is a case when all nodes are colored in 3 colors. Here we consider this to be the 3 primary colors and color the nodes black. The maximum eigenvalue is expressed a simple linear sum of the number of nodes and the number of edges. In the left graph, the horizontal axis is the value of A over B, which the ratio of the first and second term coefficient parameters when generating QUBO. B is fixed at 10. The blue solid circles on the graph are total number of ground state convergences when QUBO coefficients are embedded in D wave 10 times and quantum annealing is performed 1,000 times for each embedding. The red horizontal line is the inverse of the dynamic range. Basically, the smaller the dynamic range, the more convergences there are. The table on the right shows that the inversion seen on the horizontal axis 0.3 and 3.6 is due to the influence of the number of first excited states. The table in the previous slide has been excerpted with the number of states of the first excited states added to the bottom. The existence of the first excited state has a trapping effect because its energy is close to that of the ground state, reducing the probability of convergence to the ground state by a factor. However, the optimal parameters seems roughly balanced, in the dynamic range of the parameters used when generating the QUBO. Parallel machine scheduling program has a more complicated formula than GCP. In the previous slide, we used a two-machine problem to explain how to generate a problem that can trick the greedy algorithm. But here we will use three-machine, six-job problem by adding one more machine to show that the maximum eigenvalue becomes very large and that there is an extraordinary state. Even with ZCP, the state showing the maximum eigenvalue was an unusual one with penalty, where one node was painted with all three colors. PMSP is even more unrealistic because although there are only 6 jobs, QUBO allows a state in which 12 jobs are assigned, of course with penalty. In the figure below, the left side shows a state in which QUBO energy is minimized. That is, the make span is minimized and all constraints are satisfied. The right side shows a job assignment that maximizes energy. If you look at the equation in red, at the bottom right of the constraint equation, the third term is very large number for B, even for such a small scale problem. Therefore, unlike with GCP, you can see that the two terms will not balance unless A is rapidly increased by the square of the total process time. With GCP, the deviation in the magnitude of the terms related to A and B changes slightly depending on the problem scale, but it was not that great. With PMSP, deviations of several orders of magnitude already occur, even in small-scale problems, even that are no need to be solved or very easy to be solved. So from here on, we will use standardized A dash and B dash as shown at the top of graphs for the entire second and third terms, including the coefficients. A and B usually have insufficient constraint effect when set to 1. Therefore, A and B are set larger. The minimum gap is always determined by the first term, which has no parameters, and is usually considered to be 1. B has a large effect of expanding the dynamic range, so it set to 2. It usually has a sufficient constraint effect. In order to obtain all practical solution states, it is also effective to use state where the constraint in the third term is not satisfied. For more information on this method, please refer to the preprint. As a graph shows, the ground state convergence probability of the D wave is optimal when A dash and B dash is nearly balanced. It is not just the dynamic range that affects the convergence here. The second term, A, plays an interesting role, and the second term as an independent eigencoefficient that affects the convergence, which I want to go into the interest of time. For more details, please see the preprint also. Finally, we will introduce an example where D-wave shows straightforward ground state convergence characteristics as a number of spins increase by generating QUBOs with optimal parameters for NP programs with uniform trends. The horizontal axis of the graph shows the number of spins as a problem scale, and the vertical axis shows the ground state convergence probability. The blue squares are ground state convergence probabilities of Zephyr, and red circles are that of Pegasus. The small crosses represent exponential slopes. The number of spins on the left side varies depending on the graph, but the intervals between the spin numbers are uniform so that the slope can be compared. The PSMP convergence example on the left has a large dynamic range of the problem, and the convergence probability drops rapidly as the number of spin increases. The advantage of Zephyr is also small, make it difficult to see the difference with Pegasus. On the right is the D-wave ground state convergence probability for the graph coloring problem. We will show on the next page that the degree of degeneracy is extremely large and the dynamic range is small. As a result, the convergence probability is high and the drop with increasing the number of spins is small, highlighting the advantage of Zephyr. Quantum annealing would be effective for problems where the resolution of electrical systems is sufficient. The increase in ZCP difficulty is small, even when the number of spins increases, and the next slide will explain the relationship between the ZCP problem, difficulty, and the number of spins. This table shows the dynamic range and the number of different eigenvalues of ZCP and PMSP. If we consider that the larger the maximum eigenvalue and the more types of eigenvalues, the more difficult the problem. The 18-spin PMSP seems to be much more difficult than the 126-spin ZCP. In fact, this is consistent with the D-wave convergence results. Well, conversely, let's use this knowledge to analyze the dynamic range and the degeneracy of instances before and after reducing the number of spins in the excellent work by Santis et al., who reduced the number of spins by factor 4 and improved the convergence probability by more than 10 times. We plotted tables 5 and 6 by Santis et al. In our format. We can see that the problem before reduction had a fairly small dynamic range and a fairly high degree of degeneracy. Reducing the number of spins increased the convergence probability, but the slope has increased because the degeneracy has become much smaller. This is quite natural as a result of comparison. Okay, let's summarize. The convergence of QUBO instances used here generated from 3 NP problems is determined by the dynamic range of eigenvalues, and there is little possibility of inhibition of fast state transition, for example, by anti-crossings. QUBO generation parameters near where the dynamic range begins to increase offers best ground state convergence probability. NP problems with the properties aligned with optimal QUBO generation parameters, the change in the ground state convergence probability as the number of spins in the problem increases becomes straightforward. The smaller the dynamic range of the problem, the higher the ground state convergence probability of the annealer, and the smaller the decrease in the ground state convergence probability with an increase in the number of spins in the problem. In this case, the performance of the deferrer is obviously improved from that of Pegasus. The more complex the NP problem itself is, the lower probability of D-wave converging to the ground state becomes. As the dynamic range becomes larger, the difference between deferrer and Pegasus becomes smaller. This gives us insight into the nature of the problem. Finally, I would like to thank the members for their helpful discussions and conclude my presentation. Thank you for your attention.
Thank you for your great presentation. Now it's time for questions or comments. Are there any questions from audience? If not, I'd like to ask. So yeah, mainly two part, I think. One is without modifying the eigenvalues, but there's some trick to change the QUBO itself, as well as the second part is tuning the parameters. So those two approaches looks promising. So my question is, so are those approaches algorithms? So if that works well, we should try. But for example, the parameters, we need to test the multiple parameters or like grid search. So how much burden they are? I mean, if the burden is polynomial, it's in terms of the system size n, it's worth to try. But that prefactor of the burden is proportional to the like exponent of n. It's still we realize it's really tough. So for this kind of the point of view, so could you explain the two approaches you developed? Is what is a prefactor if we apply your technique?
Prefactor? Excuse me.
Prefactor, I mean that,
Yes.
so like the grid search, if we set to the 10 point, so that the total cost will be 10 times more. So if the system size will be twice or 10 times larger, that kind of the parameter optimization, we still just need the 10 times more D-wave run, or if the system size goes large, we need to search the parameter more preciously. If that's the case, yeah, the prefactor will increase depending on the size.
Yes, you're right. So, well, so the second part, the optimization of the parameter, well, it is not related to the size of the problem, but well, first time, and I mean, unitary transformation. Well, there are well, but the number of total number of the transformation equal to the number of spins. So the cost becomes larger, but
it's still polynomial, proportional to the system size. And
yes, but well, I wonder if well, when the transformation is effective, at that case where there are not so many first or second or lower excited states, and if there are a lot of excited states but very close to the ground state, at that case where the unitary transformation is not so effective, because it must change the energy landscape by a kind of make a shuffle. But if the energy landscape near the ground state is a little uniform. Uniform means from the small Hamming distance to larger Hamming distance, where there are many lower state. At that case, the transformation may not be so effective. But the number is polynomial, so yeah, we can use it, I think. Yeah, every transformation just for trial, it's not so cost. Yeah, it costs not so much, I think.
I see. Thank you. Any other questions? Comments? If not, thank you again, Toru, for your great presentation.
Thank you, Chairman. Thank you, everyone.
And also, I'd like to close this seminar. Thank you very much.